Hey everyone, I'm really glad to be here and talk about one of our most interesting applications of machine learning and general algorithms in energy industry, for me at least, is actually measuring solar production in the behind-the-meter solar panel installations. Please disregard like the first line. I was trying to follow Vaidas' lead with good presentation topics, I think so. but the second line is totally true. So we do what I will talk about today is how we estimate solar energy production from the very noisy signal of just exported energy to the grid. Maybe a bit on Eliq, because it's a small company and it's been less than 2 years in Lithuania. So Eliq actually is a startup from Gothenburg. It was founded around 10 years ago now by the guys very keen on energy transition. It went through several iterations from hardware production, hardware manufacturing to app building, and now we are kind of serving our users and locations through energy transition platform. So basically what Eliq does, it takes in the data, energy data, weather data, market data, and then at the end of the pipeline outflows the energy insights. And we're kind of dipping a toe into energy management with EV charging and things like that. We are a small team. We are based in Vilnius. That's a data science team. Well, technically, it's a community as we work in cross-functional product teams. Vaidas was the second who joined, and Justina, some of you might know, she actually joined us from Danske Bank a bit more than a year ago. Shameless plug, we are hiring. Yeah, a bit about myself. I actually worked at Danske Bank as well, like 6-7 years ago probably. But I'm coming from the business background. I graduated from economics and then studied finances, and as you can see, like went from one big company to another, and then started this whole startup thing, which is kind of nice actually. I enjoy it very much. Yeah, then let's go. So a bit what Eliq does. So just to put things into perspective. This is just some of the things that we produced to locations. We do similar homes where we compare your location to other locations. We do anomaly alerts if your energy consumption is a bit different from what we would expect. We do solar energy estimation, about which I will talk today, which enables for increasingly larger number of locations, energy usage categories, which are basically our estimation of where you consume your energy based purely on your smart meter data, and a bit additional data as well, actually. And then that enables, together with other services, enables energy advices where we can kind of nudge you into the direction of using less energy or using energy more efficiently, or maybe suggesting something that you should upgrade. So this is just adding some data, and I just wanted to I did another presentation a bit previously, and I wanted to include this just to kind of highlight how data science enables certain things. Basically, by having just 4 sources of data and then combining that with algorithms and different approaches to the things, we can actually do some pretty cool things. So basically, just having your hourly energy meter data and then having weather data and maybe asking a few questions about your home and what you have in your location, we can actually say like, hey, we noticed that your heating system is not the most efficient, and maybe you are on a 90th percentile of other houses who use similar heating systems. You should do something about it. So it's, yeah, it just kind of, for me, just highlights the power of data science basically and what we can do with it. But we are talking about solar energy estimation here. And for that, we need to know, so what is it? Like, what's the system that we are trying to estimate here. And something like this, I guess. We have a sun, panels on the roof. This is where the electricity gets generated, and it's basically, it can be approximated with several parameters. One is azimuth, which is basically where your panels face compared to the compass. So basically, if it's 180 degrees, it's pure south, and so forth. Another is tilt, so how like the tilt angle of the panels, as well as size and efficiency of panels. So that's basically 4 parameters. There are more, and there are a bit less maybe important, but these 4 parameters kind of define your system and how much solar energy it can generate. Now, this is what we are interested in, energy consumption. So if we want to say, if we want to do energy usage categories, like disaggregate your consumption into categories or do anomalies or anything like that, we need to know your consumption. However, if you have a PV system installed, what we see is actually this, just an import and export from the grid. So that's where the kind of the noisy signal comes in. We only know what you take out of the grid and put in, but we don't know what you consume, because that's kind of defined by this part, the energy that comes from your panel. And that's what we need to estimate, because most of these panels are actually like it's shown here, behind the meter, where you don't know, basically, or at least utilities that supply energy don't know how much electricity is generated. You need to have, like, there are quite a few of inverters, and there are quite a few suppliers, and then if you need to connect to all of them, that's kind of the dead end, basically. You cannot build connections to all of those systems. So that's a system, and that's what we kind of try to estimate. So again, that's machine learning talk. We also need to talk about data, and then we kind of have I like to think about 3 kinds of, it's a one way of thinking about data and what you have, but basically I like to think about it, what I have at test time, basically when I apply the model, so what I have now, what I have when I train a model. Basically, usually not every data that is available to you at train time will be available at test time as well. And then it's a lot of data, so it's like something very separate, that we could just third-party integration from our side. So at test time, what we have, that's kind of an example of real location. That's actually in Lithuania, of import and export energy. That's how it usually looks. So it's watt hours on the y-axis, and you basically produce, not surprisingly, in the midday, and then you mostly consume in the mornings and in the evenings. This is a bit more kind of normal looking, I would say. That one is very clean and probably some like location that no one lives, basically, throughout the day. So that's the data we have, like imported energy and exported out of it. Well, on train time, however, we have for some locations, and we need to have for some locations, also actual solar production. So this approach I'm talking about doesn't work if we don't have any real solar production data at all, and we'll talk about why in a minute. But that just basically, the purple line, basically you see it follows very nicely. This is where it looks a bit more real, actually, so just the wider gaps, and just because higher consumption at places. And then there is weather data, and I guess when you think about solar, I guess the most obvious weather data feature is cloudiness. So if it's cloudy, there should be less solar generated. If it's not cloudy, I guess more, or at least at the potential. As you can see, it's also not perfect. Like this point at 13 hours, 1300 hours, it's kind of no cloudiness according to our data source. However, it clearly is not at the potential. So it's like always, data has its issues, weather data as well. What we found with weather data, actually, if you try to query APIs too hard, you get a lot of nuns as well. So sometimes it's just kind of the provider cannot serve your queries fast enough, and therefore you get data quality reduction, basically. So we in production, we even have to kind of reduce the amount of queries we send to actually get better quality data, because it's kind of search on the end. Yeah, that's similar. And as you can see, like at 9 in the morning, cloudiness is high, and therefore you see a dip in production, which is kind of very obvious. Yeah, and then other weather data that is important. Temperature is very important. Temperature is important for panels to actually operate at their max capacity. And then they usually have quite low efficient point, because all the heat that is generated as well for connection. Precipitation is actually not the second most important thing. Humidity is, but I think you could say that anything that impacts atmosphere in a way that can scatter light basically impacts efficiency as well. And that's why we'll see later, like other features, like for example, month of the year is also kind of important feature in modeling these effects, which I guess just kind of captures all the effects that you usually see during certain months. Now, the algorithm that we feed this data is actually called Sundance, which is a very cool name, I would say. And when I found it, it's very practical algorithm in general. It has two parts. One part is location specific, so you need to do something for each location, and that's where it's not 10 ml per se, like you cannot train one model. However, there is a generic weather part effects where you kind of training ML model, and and where you can then get transfer across the locations. So, what do you train ML model for? Here is again, purple line is your produced solar energy. Then the green line is actually estimated potential solar energy in the ideal conditions. And I'm actually scrambling it a bit, because you need to run the location specific part first to actually then run machine learning model, because what we are trying machine learning model to learn is actually this utilization rate, the red line. That's what we are interested in. So we can produce the ideal conditions solar energy for each location when you train the models, like without even any data. But then to actually get the actual production of solar energy, we need to know, given the certain conditions, time of day, maybe time of year, like what's the utilization rate would be expected at that particular location. Well, actually at all locations that you train a model on. We kind of have these models based on country for now, or even for client basically. So that's what we are modeling. We are modeling utilization rate. We are modeling when it's high and when it's slow. This is how it looks for the same location, just kind of October data. So as I told before, in the paper, it's actually called weather effects model. And basically they try to model only through weather features. But what we found through our work is that not only weather affects it. So for example, as you can see, imported energy and exported energy has quite a big correlation with solar utilization. And it makes sense if you think about it. If there is a lot of imported energy, usually it means that there is less production during that hour, for example, or 15-minute period. And for example, if it's a lot of exported energy, that's kind of vice versa, like you probably produce quite a lot. And that's kind of all the weather features have quite significant correlation as well. And as you can see, I include the hour and month. And that's where it came, like, I found that accuracy of the model increases quite a bit if you include those features, basically which month of the year it is, what hour of the day. Somehow it doesn't overfit by any means, but like it helps a lot. And then, yeah, for us, it's actually just a regression then. Like we treat it as a regression problem where you can apply, I don't know, any regression model you want, would like. And yeah, we just treat it like that. We cap it, of course, 0 and 1. Kind of doesn't make sense any other, but that's how we do. That's how we treat this. And then there is this location specific part, which is, yeah, it looks better when you look at it on a computer. But what it basically says is that like 3 parameters, beta, and k, is basically tilt, azimuth, and model efficiency of size, which is basically a combined parameter because it's some multipliers, 2 multipliers, and you kind of have one, you can have separate if you like. Influence how much power is produced at your PS is power at your solar installation. And I stands just like for general solar irradiance at your location. The interesting or cool thing for me, because I'm coming from the economics background and you don't have any kind of real constraints on your kind of problems. It can be like anything basically. Here you can calculate, there are quite good models where you can calculate how much solar energy there will be at any time and day at any point in the world, which basically gives you the like that curve, and then because of that you can fit that curve onto your data quite well. So that's like that's the neat trick, and it's not the trick, it's neat the feature of this problem, that given you have like actual physical constraints on the system, you can actually quite well model quite well the solar production. Yep. So, and that's what the impact is basically, just kind of an illustration from the paper, which is very nice. Orientation. If you change orientation, the peak production time just differs a bit. Like if you took it to the east, of course, the peak will be more towards the morning, and similarly, size and effect. The middle graph, the bigger the size and the bigger the efficiency, like the higher the production. Tilt has a bit interesting effect actually, if you can see from the graph, because it's and actually the combination of those two is what kind of is tricky to model, and I think it's not intuitive like how these parameters interact with each other if you increase one and decrease the other. And that's where the bottleneck of this algorithm actually for us, like it's technical details now, which are very interesting for me, is that you have 3 parameters with quite a lot of values, and you need to search that space to find like the best combination of those. And it's quite a big space to search for, and especially if you're trying to brute force it. We haven't tried very smart like Bayesian optimization things yet, so therefore we kind of went old school ways, I guess, about this. One is actually to use less data. That's a bit counterintuitive, I guess, but the interesting thing, if you think about it, you have like this predefined curve of your solar production and how it looks like throughout the year. You can generate it like for years and back and forth. And then you have your data, and you just try to kind of fit like that as an upper bound, that curve, you fit as an upper bound of your data. But you don't need all the data you have. You just need the data that defines your production system very well. Therefore, when you are not at home, you export everything, probably what you produce. And the best case scenario is actually when you can find these days throughout the year, so in different months, that you can capture like different dynamics at different solar positions and when it rises and stops. So, and that's actually illustrated here quite well. Like if we have like the whole year 15-minute resolution data, it takes 9 minutes to run on, this is done on 48 core machine we just use Joblet parallel, basically engine, the lock engine that Python uses to distribute the work. It took us 9 minutes, and it's a no-go. If you have several thousand locations that you need to find these parameters and you need to do that several times a year, so it's just like there is no way that you're going to keep up with the work. So what we tried is actually reducing the number of days, and the best approach we found, and I say we, but actually that's Justina who did the work. The best approach we found was actually 3 days each month with the best solar production, plus another 10 days. And 10 is kind of an arbitrary number, but you can pick whatever. Just we want to capture best performance of that location in terms of energy production throughout the year, to capture these curves in different kind of periods, plus some additional days where it's actually very high production. So therefore we could match the curve to actually to those times when it produces most, and therefore gives us least error, like in yearly terms. So, and that's basically 12 times as bad. Like it was amazing. Like when we found this, like we said, okay, so we are safe. Like cloud bills won't kind of sink the company now. And then another trick, it's not a trick, but it's neat that just by changing the compute engine you use can reduce the running time so much. So first we just used, I don't know how many of you are Python developers, but you just Joblet parallel, which uses Locky engine. It's a way of kind of bypassing Jill. And then Ray is actually kind of an actor system, I think, kind of implements it in Python. And it reduced it like in half, it took our running time. So that's, again, like 20 seconds for training each location is still a lot of time, but now it's kind of, at least it's feasible to do it like in a business sense. And then once you have all that, it's interesting to see what you can do. So what are the results? For us, when we tried first time, I think we have it a bit worse. We improved. We did a few more tricks here than just what I said. But basically, this is for 68 locations with P installations, 1 year of data. If we run our algorithms and we train models on the month aggregation, basically we took all the month energy produced and just added it all up. We took all the energy that was estimated for the month, added it all up. We average absolute percentage error is, and then average out for all the 69 locations is 10%. So basically taking just imported and exported energy and then weather data, and you can re-engineer the consumption. Consumption re-engineering comes from just kind of this algebraic relationship between production and the import and export, but basically with 11% accuracy, absolute percentage error on average. This is, for me, I was very surprised basically when we saw the results. And for clients, it's also reassuring as well, because especially utilities, and probably you guys from the bank kind of can feel the sentiment, they don't like to make errors, and we don't like to show very uncertain numbers to the user. So they're very strict on like what to show and what to know, and we need to kind of, we need to devise indicators, which location to show and not to show, these estimates, etc. But yeah, for me, it's kind of cool. And then the location I showed you before, this is actually the estimated, and the red one is the actual number. And I tried actually looking up, this is again Lithuania location. I tried looking up some very weird ones, but for the Lithuanian part, we kind of did quite well actually. So, but there are quite bad looking graphs as well. So that's I know that's the same location, just different times October, since they have a lower curve. But it looks really good basically. So it's Yeah, for me it's still kind of cool to see that it works basically. Well, I guess for physicists it's kind of normal, like physics works, like, yeah, what do you expect? But like, yeah. So takeaways from this exercise, should be takeaways. If you have a physical constraints on your system, it's like, for me, like, I don't know, it was eye-opening basically, but it's very, like, it helps a lot basically for your estimates. You can, like, ML is very good at estimating something that is across different units. For our case, it's locations. So it's, without ML, we wouldn't be able to actually have a good estimate, because we need to have this ML model for weather and other impacts. And probably the most important takeaway is that's from the very good paper from Google, Hidden Technical Depth and Machine Learning. But basically, machine learning code is usually just a very tiny part of what you build. And therefore, in our case, it's also just kind of one model, just for part of a problem. And most of our code that is written for a PV system is actually optimization of the PV parameters, like making sure that we gather them, making sure that we version them, making sure that everything runs, etc. So I think being an ML conference is maybe not the takeaway to give, but basically, especially in a startup environment, you cannot actually overinvest in that part. If it doesn't work, if you try something quite simple, maybe you need to find another approach to that problem, and therefore that's what we did. We tried, it worked approach, and we didn't go forward and kind of tuning every little in detail. But while I know that there are tons of details to tune there and even different approaches, etc. So yeah, thank you, and hopefully you enjoyed it.